Alright, so in this video I want to talk about self-attention. So along with self-attention we will talk about what is multi-head attention and also masked multi-head attention. So these three concepts are quite essential if you want to understand what is sliding window attention. So to understand the sliding window attention, which I will talk about in the next video, let's first talk about what is self-attention. Right, so in case of self-attention, right, so we generally have this encoder decoder architecture when we are like doing a machine translation task. So when we are like passing one language to the encoder side, so this can be a language called Bengali, and that we are passing to the encoder side. Each of this one by one we are passing each of the tokens of a particular sentence, and then we are like kind of calculating the hidden states like h1, h2, h3 and h4. Then h4 once we generate that will kind of act as a context vector, and that we will pass to the decoder to generate the further tokens in a different language. So that language can be English, right? So if you are new to this concept of encoder decoder and how this sequence to sequence model works, I have a few of the details videos from my deep learning with PyTorch playlist. So I will also mention the link of those videos in the description of this video, so you can go ahead and get your concepts cleared with those videos, right? So the problem with this sequence to sequence model is we are expecting a lot from this context vector, right? So we are expecting this context vector to like incorporate all the hidden states which are here, right? And with that hidden states incorporated in the context vector, then we are translating it to a different language. That can create a lot of problem, but what I have talked about in my deep learning with PyTorch playlist, so you can go ahead and look into those videos. Now to tackle this, what we can do is we can make this a few changes in this architecture. So what we can do is, instead of only depending on the h4, we will also incorporate the other states, or we will also make available all the other states from this encoder side for the context vector, right? So, and along with that we will also calculate attention score. So if for an example, like if y2, when we are translating a particular language to another language, and for a particular token like for y2, if that has more emphasis on a hidden state which is associated with h3, right? So the attention score will be higher for this h3 for y2, right? So each of these individual states, each of these individual tokens will get a context vector like c1, c2, c3 and c4, right? So all this will get an individual context vector, and then with that it can like using the attention score, it can like put more emphasis on certain parts of the input sequence, and with that the translation will happen in a much better way, right? So this is what a basic concept of self-attention is in case of encoder decoder architecture, right? Now let's try to visualize this this basic form. So what we generally have is we have this xi, which is my current input, and for that we are kind of calculating the dot products between xi to the all other input tokens, which are like x1, x2, x3 and xt. Then once we calculate the dot product, so this dot product is kind of gives you the what is the similarity between these two tokens, and once we have those dot products, then we can normalize using a softmax, and after that we can calculate more context aware embedding vector for xi, right? So this is like using this j equals to 1 summation to t multiplied by aij. With xj we can calculate the ai, so that is kind of a more context aware embedding vector for the xi, right? So this is a very basic form of self-attention, where we are kind of, first of all we are doing a dot product, then normalizing using a softmax, and then we are calculating the final embedding vector, which is more context aware, right? So here you can see there is no learnable parameters in this approach, right? So what we can do is we can now bring in certain learnable parameters through which while doing the back propagation in this neural network, it will also learn those parameters during the back propagation. So we have three trainable matrices which are like WQ, WK and WV, right? So this three trainable matrices are multiplied with the input sequence to get the query key and value, right? So we get the query vector, or the query vector by multiplying wq with xi. Then we have the key vector and also the value vector, right? So what we are doing is we are passing the x, and x is getting multiplied with wq, wk and wv, and we are getting the corresponding QKV, right? So this query key and value, this concept came from the attention is all you need paper, and that is kind of the learnable parameter which we have introduced in this architecture, right? So once we have this matrices, what we do is we do this operation, right? So at first we multiply Q with K transpose. Then to minimize the variation of this, the variance of this multiplication of Q multiplied by K transpose, if we don't like divide this with the root of the dimension of K, then we will get a huge variance of this multiplication, right? So just to minimize the variance of this multiplication, we are like dividing this QK transpose by the square root of the dimension of K, right? Here, just for an illustrative purpose, I am taking an example like this is my input sequence, which is like attention is all you need. So the length of this sequence is 5, right? Then we have this K, which is the embedding size, right? So embedding size is like for each token, right? So if I talk about this attention, it will be represented with a long stretched out vector, and this shape of this is K, which is usually in attention all you need paper is 512, right? So with that, what we will do is, let me first clear this. Okay, so what we will do is we introduce the Q matrix, which is n cross K, and then we multiply with like K transpose, which like after doing the transpose, the shape is K cross N. Now we are multiplying n cross K with K cross N. So, and then we are dividing by the square root of K, right? Just as I mentioned, this is to reduce the variance of this dot product, right? Then what we are doing is we are doing a softmax on top of this whole operation, and we are getting a output. This output is nothing but a attention based matrix, and that the shape of that is n cross n, right? So this is what we call as attention based matrix, where each part of the token is kind of have a attention score associated with a different the other tokens that are present in the input sequence. N is nothing but the sequence length, right? So if I just take this example, so we have this n cross K, which is our Q. So this is like 5 cross 512, right? So as I mentioned, like in attention is all you need in paper, this K is equals to 512. So for this example, the shape of Q is 5 cross 512. Then we are multiplying with, like after doing the transpose, we are multiplying with a shape of 5 cross 12 cross 5, and then we are like dividing it by the square root of K, and then we are taking the softmax, and what we are getting as in the output is 5 cross 5 attention based matrix, right? So n is nothing but the sequence length which we are mentioning here for this example. So after that, what we are doing is we have done the first part, like doing the softmax operation on this after doing the dot product. Then we need to multiply this with the value vector, right? So we got the attention matrix, which is like this n cross n matrix, and that we will multiply with V. So V is nothing but a shape of n cross K. So we are multiplying n cross n with n cross K. So the output what we will get is n cross K, right? So this what we call as embedding vector, and this embedding vector is much more context aware. So we are calling this as attention based embedding, right? About what is multi-head attention, right? So we talked about self attention, and now let's talk about what is multi-head attention, right? So in the multi-head attention, the concept remains the same, just that we are having multiple heads which we will calculate using the formula that we have already talked about using the attention mechanism, right? So we have our input. That input is get multiplied with the different learnable matrices which are like WQ, WK and WV, and we get the corresponding query key and value vectors. So once we have that, what we will do is we will divide each of these matrices, like the Q will be divided into 3 matrices like Q1, Q2 and Q3, right? So we are kind of introducing this multi-head by dividing the Q to multiple heads, right? So similarly we will do that operation for the K matrix and also for the V matrix. So we have corresponding K1, K2, K3 and also the V1, V2 and V3 for Q1, Q2 and Q3. Now we do this attention operation. Using this formula, we will calculate each of these heads, which are like H1, H2 and H3, using the same formula which I already talked about in the last few minutes. And after that, what we will do is we will concatenate each of these heads like H1, H2 and H3, and that gets multiplied with a output matrix which is WO, and we get the multi-head attention, right? So in one head it may be picking up certain characteristics of the input sequence, and using multiple heads we assume that it will pick up the other qualities of the input sequence, and it will be more diverse in terms of calculating the attention of the for different characteristics of the input sequence, right? So once we have this multi-head attention, then let's talk about the masked multi-head attention, right? So why we need first of all the masking, right? So in case of encoder side, right, so this is the encoder side example. Your any of the tokens, right, if I talk about this all token, right, so that token can look into the past tokens, the previous tokens, and also it can look into the future tokens, right? So this is what it can happen in case of encoder side, because encoder side we are mainly generating the embeddings, and embeddings can look at the past behavior of the input sentence or the input sequence, and also it can look ahead for the future tokens or the future words for the particular input sequence or input sentence, right? But it is not the case if when we are talking about the decoder side, right? So this is what we have talked about the encoder side. In decoder side, it is mainly the decoder is trained for next token prediction or the next word prediction, right? So we need to mask out the future tokens for each of these sentences, each of these tokens, right? So for attention token, it can only look at till this part, and after that it is all zero, right? So because it cannot look ahead what are the tokens that are coming in the future. If it looks into the future tokens, that is kind of cheating, right? So just to avoid that, we will mask out these tokens, and we will make all the future tokens for a particular token as zero. So for like is token, it can like this values will be masked out to zero, and similarly for other tokens the future values or the future tokens are masked out to zero, right? So all this value which I am showing here, you can see like the diagonal elements are kind of highlighted because that is kind of a word is looking into itself, and those are using a self-attention mechanism. Those attention score will be much more higher, but these values are random, so I have like used random values in this matrix. So don't think like why the values are not adding up to 1, because after doing the softmax, each of these row wise elements will be summed across summed equal to 1, right? What we do in case of self attention for this decoder side is, or the causal masking we also call it, we will make these future tokens as minus infinity, right? So once we make these future tokens as minus infinity and then apply the softmax, these values will become 0, right? So this is the concept of like masked multi-head attention, and this we will do for all the other heads. So this is for one head, and that operation similarly we will do for the all the other heads that are coming from the masked multi-head attention mechanism, right? So with this, I hope you got an understanding of all this concept which I have talked about the self. So with this, I will end this video. I hope you got a good understanding of this mechanism, and this will help you to understand the future videos of this series. If you haven't subscribed this channel, please subscribe and share this content with your friends and colleagues. Thank you. See you in the next video.